A digital laser thermometer points directly at raw red sandstone, baking under the unyielding desert sun 142.8 degrees Fahrenheit. The air above the rock shimmers in thick, distorting waves, smelling of scorched dirt and overheated sagebrush. Now, picture this. You take just 3 steps backward, ducking beneath the shadow of a massive, 80-foot natural sandstone cliff overhang. Point the laser at the shaded rock surface 88.2 degrees Fahrenheit. Then, point that same infrared laser at the exterior timber wall of a hand-built off-grid cabin tucked neatly beneath the canyon shelf 64.5 degrees Fahrenheit. Inside that cabin, there is no humming air conditioning unit. There are no massive solar-powered chillers, no noisy generator banks, and not a single wire connecting the structure to a municipal power grid. Outside, the high desert is a furnace, capable of killing an unprotected human in a matter of hours. Inside, the air feels like a crisp mountain morning in autumn. Think about that for a second. While standard off-grid homesteaders spend tens of thousands of dollars on complex battery systems and massive solar arrays that frequently overheat and fail when ambient temperatures surpass 115 degrees, this structure stays impossibly cool, using nothing more than raw geometry and the fundamental laws of physics. Here's what everyone missed. This is not a story about modern technology saving the day. It is the story of a solitary builder who rejected high-tech quick fixes to construct an immovable thermal fortress directly against an ancient cliff wall. But doing so meant facing a hidden engineering paradox that almost destroyed the entire project. Building a living space beneath a massive rock canopy creates a deadly microclimate, a stagnant dead air zone where invisible, odorless carbon monoxide gas can pool, trapped above your roof until a silent backdraft fills your sleeping quarters. To survive, this structure could not simply copy the past, it had to re-engineer it. The numbers don't lie, and over the next hour, you will see the full thermodynamic breakdown, the raw sensor telemetry across all 4 seasons, and the precise mechanical specs engineered to withstand both 115-degree heat waves and sub-zero Arctic blizzards. If you appreciate deep-dive off-grid engineering and survival mechanics, hit the subscribe button right now, because what this structure proves about passive design changes everything we thought we knew about building in extreme environments. To understand why this cabin works, you first have to understand why almost every traditional off-grid build in the high desert fails completely within its first 3 years. Out here on the Colorado Plateau, in the high desert canyons of San Juan County, Utah, nature does not negotiate with builders. The sun is not just a source of light. It is a continuous thermodynamic assault. Surface temperatures on exposed timber and sheet metal routinely cross 150 degrees Fahrenheit during peak summer months. When modern off-grid builders try to set up a homestead in this environment, they almost always rely on standard stick-frame lumber construction or prefabricated metal shells, and that is where the disaster begins. Sheet metal roofing acts as a direct thermal conductor. Under the intense rays of the high desert sun, a metal roof absorbs heat rapidly and radiates it downward directly into the interior ceiling cavity. By 1 o'clock in the afternoon, the inside of a conventional unconditioned metal cabin turns into a literal oven, reaching interior temperatures well over 120 degrees Fahrenheit. Wooden structures fare little better. The extreme daily temperature swings of the desert create a brutal cycle of thermal expansion and contraction. During a single 24-hour period, temperatures can shift from 40 degrees Fahrenheit at night to over 110 degrees during the heat of the day. As the materials expand in the scorching afternoon heat and contract rapidly during the freezing night, nails loosen, structural joints shear, weather stripping rots, and timber framing warps out of alignment. Within 2 or 3 seasons, sealants crack open, letting stinging dust and blistering heat pour into every seam of the home. Let that sink in. The harder modern homesteaders fight the desert heat using standard building materials, the faster the desert destroys those materials. Historically, the people who survived this landscape hundreds of years ago knew better than to fight the sun out in the open. 12th-century ancestral Puebloan builders constructed massive stone cities underneath natural alcoves and cliff overhangs, such as those found throughout the American Southwest. 19th-century homesteaders later followed suit, building rough timber shelters under sandstone shelves to escape the brutal summer months. These ancient builders recognized a fundamental solar reality. In the high desert, direct sunlight is your primary enemy. Natural sandstone overhangs act as massive solar umbrellas. During the hot summer months, when the sun is high in the sky, a deep overhang blocks up to 95% of direct solar radiation from ever touching the structure beneath it. Yet modern DIY builders who try to replicate these historical cliff shelters almost always make a fatal structural error. They assume that simply pushing a cabin up against a canyon wall or sealing a timber framework directly into the stone cliff face will instantly grant them free natural cooling. They could not be more wrong. Building directly against raw sandstone introduces three severe, hidden hazards that ruin traditional structures. First, raw sandstone is dynamically active. Moisture traveling through the rock matrix slowly seeps outward, creating constant dampness, toxic mold, and mineral efflorescence behind sealed walls. Second, natural freeze-thaw cycles cause the cliff face to expand, shedding heavy fragments of rock that can crush standard timber roofing. And third, and most dangerous of all, raw sandstone holds heat differently than the surrounding air. When hot air accumulates beneath an alcove without proper ventilation, it becomes trapped in a dead air pocket, creating a stagnant heat dome that bakes anything resting directly beneath the canopy. Without a total rethink of passive thermal isolation and mechanical airflow, building under a rock is not a solution. It is a structural trap. To overcome these environmental hazards, the builder had to throw out conventional construction manuals and execute an entirely original engineering playbook. Phase 1 began high above the ground, scaling the ancient red sandstone canopy with ropes, pry bars, and mechanical expansion anchors. Before a single timber could be cut, every loose slab of rock hanging within 30 feet of the proposed roofline had to be systematically cleared. High desert sandstone, weathered by thousands of years of frost and intense heat, can suddenly spall flaking off in heavy knife-sharp sheets. Scaling the wall removed hundreds of pounds of loose talus, ensuring the space beneath was structurally safe for long-term habitation. Next came the critical mapping of the canyon drip line. During sudden desert monsoons, water does not gently rain down beneath an alcove. It collects on the plateau above and pours over the edge in a raging, continuous water curtain. By standing on the site during a massive late summer storm, the builder precisely mapped the exact line where the water fell from the cliff edge, ensuring the cabin's footprint was set back safely behind this natural aquatic boundary. Phase 2 involved laying the foundation, and this is where most off-grid builders make a catastrophic mistake. Here's what everyone missed. If you anchor a cabin's floor frame rigidly into both the dynamic bedrock floor and the vertical cliff wall, you create a rigid bridge between two massive geological bodies, moving at different rates. As the canyon floor warms and cools, it expands independently of the deep cliff face. A rigid anchor will literally shear steel bolts in half or crack a concrete pad within a few seasons. Instead, the builder engineered a decoupled, floating foundation system. The heavy floor joists rest on high-density concrete footings, lined with thick, closed-cell elastomer thermal pads. These pads act as heavy-duty vibration and thermal isolators, allowing the wooden chassis of the cabin to float micromillimeters above the rock floor without transmitting structural stress or drawing damp frost directly up into the subfloor. Phase 3 was the execution of the ultimate passive heat barrier, the 4-inch secret air gap. The builder constructed the cabin's rear timber wall completely independent of the stone cliff. Between the rough red sandstone and the insulated interior wall lies a continuous 4-inch open-air cavity extending from the foundation to the roofline. Think about that for a second. This 4-inch gap serves two critical mechanical purposes. First, it prevents the raw sandstone from touching the cabin walls, eliminating conductive heat transfer and stopping moisture from seeping into the timber. Second, it creates a natural convection chimney. As the rear sandstone absorbs subtle radiant energy, the air within this narrow 4-inch cavity warms slightly, expands, and rises. Lower intake vents near the floor draw cool, floor-level air into the gap, continuously sweeping heat up and out through upper exhaust vents past the roofline. Phase 4 was the alignment of the roof geometry. The roof was framed at a steep 12-degree pitch, slanting forward toward the mouth of the alcove. Rather than touching the rock overhang above, the metal roof stops 6 inches below the stone ceiling, fitted with flexible silicone weather flashing that seals out wind-driven dust while allowing the overhang to shed water cleanly past the cabin's front porch. Phase 5 focused on insulating the exposed walls, the surfaces pointing out toward the blistering desert basin. While the rear wall relied on the stone cliff and the convective air gap, the front and side walls were framed with thick 6-inch studs filled with high-density mineral wool insulation, achieving a rating of R21. The windows were custom-fitted with double-paned, argon-filled glass, coated with a specialized low-emissivity layer designed to reject long-wave infrared heat, reflecting off the canyon floor outside. The structural envelope was complete, but now the real danger began. The cabin was sealed beneath a stone canopy, and winter was coming. To safely live inside a structure built under a rock overhang, you must master the invisible behavior of heat, air pressure, and deadly gas. The core thermal engine of this cabin relies on a geological phenomenon known as the thermal flywheel effect. High-density red sandstone weighs approximately 140 pounds per cubic foot. A sandstone cliff wall 20 feet thick represents an almost infinite heat sink. In the dead of summer, direct sun strikes the top of the plateau above, but that thermal energy takes 8 to 12 hours to migrate through 20 feet of solid rock. By the time the peak heat reaches the interior alcove, it is 2 o'clock in the morning, when the outside ambient desert air has already plunged into the cool 60s. During the daytime, the deep stone wall remains at the regional annual mean temperature, a steady, refreshing 62 degrees Fahrenheit. The rock wall acts as a massive thermal stabilizer, constantly soaking up heat from the air inside the cabin during hot days and gently radiating warmth back into the space during cool nights. However, this massive stone shield creates a terrifying life safety hazard that nearly ruined the entire project. Underneath a deep rock overhang, natural air circulation drops to near zero. The stone canopy forms an upside-down bowl that traps warm air, moisture, and carbon monoxide exhaust. When you ignite a wood-burning stove inside a standard room, warm air rises up the chimney flue, creating a vacuum that pulls fresh air into the room through small cracks around doors and windows. But inside an alcove, the ambient air pressure beneath the rock overhang can drop, creating a dangerous localized low-pressure zone. If you light a standard wood stove in this environment, the low ambient pressure under the rock canopy will pull air back down the chimney. Instead of exhaust smoke rising up and out into the sky, toxic carbon monoxide gas is sucked backward out of the stove, rapidly filling the living space with lethal, invisible fumes. The numbers don't lie. Carbon monoxide poisoning under rock shelters has claimed the lives of careless campers and homesteaders for decades. To solve this life-threatening paradox, the builder had to execute a strict two-part YMYL engineering mandate. Requirement 1 was the installation of a completely sealed combustion air intake. The wood stove inside the cabin was not allowed to draw a single cubic inch of air from inside the living space. Instead, an isolated 4-inch steel intake pipe was routed directly from the bottom of the stove's firebox, through the insulated floor, and out beyond the perimeter of the rock overhang to draw clean, oxygen-rich outside air. This completely isolated the fire's combustion cycle from the room's interior atmosphere. The stove breathes fresh air from the open desert outside, burns its fuel efficiently, and eliminates any possibility of creating a dangerous negative pressure differential inside the cabin. Requirement 2 was the re-engineering of the exhaust flue pipe. A standard chimney pipe rising straight up from the cabin roof would terminate underneath the sandstone ceiling, discharging toxic smoke and carbon monoxide directly into the dead air trap beneath the rock shelf. To prevent this fatal hazard, the builder constructed a custom, heavy-gauge, stainless steel exhaust pipe lined with double-wall ceramic insulation. The flue rises from the stove, turns at a smooth 45-degree angle, and extends horizontally 6 feet out past the drip line of the rock overhang before turning vertically into the open sky. By extending the chimney tip past the canopy boundary, the exhaust discharges directly into the natural atmospheric updrafts sweeping up the canyon wall. Smoke and carbon monoxide are instantly caught by rising desert winds and carried safely away from the mountain, leaving zero toxic residue beneath the stone arch. To verify the system's absolute safety, the builder installed dual industrial-grade carbon monoxide detectors equipped with electrochemical sensors at both floor level and sleeping loft height, backed up by continuous digital pressure sensors tracking indoor to outdoor air pressure differentials. With the thermal flywheel engaged and the lethal gas hazard engineered out of existence, the cabin was ready for the ultimate test, an unprecedented weather disaster that would shatter weather records across the region. In early January, the ultimate test arrived. A historic Arctic polar vortex swept across the high desert of the Colorado Plateau, breaking decade-old weather records. Within less than 18 hours, the weather shifted from a mild autumn afternoon of 75 degrees Fahrenheit down to a punishing, sub-zero hellscape of -10 degrees Fahrenheit, -23 degrees Celsius. Gale-force winds screaming across the desert plateau reached 60 miles per hour, whipping dry, powder snow into whiteout blizzards. Driving ice particles rattled against the cabin's double-paned, low-emissivity glass like handfuls of gravel. Outside the alcove, the desert world was rapidly freezing solid. On the plateau above, melting snow from the day before trickled down toward the cliff edge, where it hit the sub-zero wind currents. As night fell, massive razor-sharp icicles began forming along the outer lip of the rock overhang. Within 12 hours, those icicles merged into a thick, solid curtain of shimmering ice hanging directly in front of the cabin facade, a solid wall of frozen water over 3 feet thick, sealing the mouth of the alcove off from the open desert. Now, picture this. The cabin was now completely encased inside a frozen stone pocket. The icicle wall blocked natural airflow across the front of the site. If the chimney design was flawed, if the external intake pipe froze shut, or if draft pressure dropped, toxic smoke and carbon monoxide would backdraft into the cabin within minutes, suffocating anyone inside. Inside the living room, the builder watched the digital pressure sensors. Outside, winds howled against the cliff face, but beneath the rock canopy, the air remained calm. The custom stainless steel chimney pipe, extended 6 feet out past the drip line, protruded completely through a gap in the icy curtain into the open-air currents. Even as ice built up along the overhang, the angled, double-walled, insulated flue maintained a powerful, unbroken thermal draft. Clean oxygen pulled continuously through the isolated floor intake, feeding the wood stove's sealed firebox, while every trace of exhaust gas was swept out and away into the storm. Then, the second miracle of passive engineering took over. The thermal flywheel worked in reverse. While the outer surface of the cliff wall dropped to -8 degrees Fahrenheit, the massive interior sandstone wall behind the cabin, insulated by the 4-inch convective air gap, retained the thermal energy it had absorbed over months of autumn sunlight. Deep within its 20-foot mass, the stone was sitting at a stable 56 degrees. Instead of sucking heat out of the cabin, the giant sandstone cliff acted as a continuous, radiant space heater. Think about that for a second. While traditional off-grid homesteaders nearby were burning through hundreds of pounds of firewood per day just to keep their pipes from bursting in -10-degree weather, the builder inside this cliff shelter burned only 3 small logs of pinyon pine every 6 hours. The indoor air temperature stayed at a steady, comfortable 68 degrees Fahrenheit. The floor remained warm to the touch. There were no freezing drafts, no iced-over interior walls, and no toxic smoke pooling under the rock canopy. The storm raged for 3 full days, burying the high desert under 3 feet of snow. But inside the cabin tucked beneath the ancient cliff overhang, the winter frost never touched the builder. To prove that this cabin's performance was not an anomaly, the builder installed high-precision digital data loggers both inside and outside the structure, recording temperature, relative humidity, and air pressure every 15 minutes for 365 consecutive days. The numbers don't lie. During the hottest week of August, when ambient air temperatures in the open basin reached a scorching 114 degrees Fahrenheit, the bare sandstone cliff face, exposed to direct sunlight, reached a surface temperature of 144.2 degrees Fahrenheit. The air temperature underneath the rock overhang dropped to 86.1 degrees Fahrenheit. The rear sandstone wall surface inside the cabin measured a cool 62.3 degrees Fahrenheit, and the living space indoor air temperature remained at 67.5 degrees Fahrenheit. During the coldest week of January, when the Arctic polar vortex plunged ambient outdoor air down to minus 10 degrees Fahrenheit, the outer cliff face dropped to minus 8.4 degrees Fahrenheit. An uninsulated rock shelf outside measured 12.0 degrees Fahrenheit. The interior rear rock wall surface maintained a surface temperature of 56.8 degrees Fahrenheit, and the indoor living space air temperature stayed at 69.1 degrees Fahrenheit with only minimal stove operation. When you run an energy audit on these figures, the contrast is staggering. A conventional off-grid dwelling of identical square footage, built in this exact desert location, requires roughly 4,500 watts of continuous air conditioning power per day in summer and constant electric or propane heating in winter. This cabin consumed exactly 0 watts for thermal control, 0 batteries drained, 0 solar panels covered in dust, 0 mechanical moving parts to break down in the middle of a desert storm. Just pure, unyielding physics aligned with spatial geometry. Here's what everyone missed. True off-grid independence is not about buying bigger solar arrays, buying larger lithium battery banks, or brute forcing your way through harsh weather with high-wattage machines. Modern technology is fragile. It degrades, it overheats, and it fails when you need it most. True survival is about working with the immutable laws of nature, rather than fighting against them. It is about understanding thermal mass, airflow pressure, solar angles, and structural isolation, using the Earth itself as your primary engine of life support. When you align your architecture with the mechanics of the natural world, nature ceases to be an enemy trying to destroy your home and becomes the very shield that protects you. However, a vital safety warning must be stated before anyone considers attempting a build like this. Building beneath natural rock overhangs or inside rock alcoves carries severe, life-threatening real-world risks. Sandstone formations are subject to unpredictable dynamic rockfalls, seismic shifts, structural spalling, and sudden flash flood channels that can wash out foundations without warning. Furthermore, as demonstrated, building under a rock canopy without specialized, direct air combustion intakes and custom flue extensions past the overhang drip line creates a lethal risk of carbon monoxide poisoning and smoke accumulation. Never attempt an alcove structure without first commissioning a comprehensive geotechnical rock stability audit, consulting local building codes, and having a certified HVAC and chimney safety auditor inspect your ventilation systems. When engineered with absolute mathematical precision and deep respect for the land, a cabin built under a rock is not just a shelter, it is an unyielding fortress of physics, standing silent, cold, and safe, while the desert heat burns outside.